Alright, Math 3, Practice 2B.2.3, Solving Systems of Equations. So, systems are just two or more equations, and we find where they intersect. Now, when we're not dealing with equations that are linear, basically the best thing to do is graph them, okay? So, I use Desmos, but you could use our graphing calculators. We just graph them, find where they intersect. So, number 1. Actually, apparently we're going to start with number 4 because that's a screenshot I grabbed. So, the black one, you can see that rational. The blue one is our linear. They intersect at -3, -3, and at 1, 1. So, there's the 2 points of intersection. There are the answers. Now we look at number 5. Or number 3, I mean. So, number 3, the black is that. Blue is up here. See, we have 3 points, so 2, 4.5 is a solution, 8, 3, and 15, 1.25. Okay? And that's really all there is to it. You just graph it and then find where they intersect. And Desmos is an excellent tool for helping us out with that. Here's problem number 2. So we can see we have an intersection point at 1, 6 and 4, 7. Now you may have wanted to zoom out on some of these to see if you can see any more, but here's our 2 points for number 2, and finally we'll look at number 1. And here's number 1 with our linear and rational, so 2, 1, and -0.278, -5.833. Okay, so when you have the equations, just graph them, and there you go. Now 5 and 6 says, look at these two functions and use those. So, the table shows us this, these x values of x. There's the values of their y values for f of x and g of x. Based on this information, what can we conclude about solutions to the systems of equations defined by f of x and g of x? So, they'll intersect at points that are the same. So notice, g of x is 330, f of x is 136. As we keep going, what happens? Well, between -4 and -3, now all of a sudden f of x is bigger than g of x. So right there, in between here, that's going to be a point of intersection. So between -4 and -3 somewhere, point of intersection. Then this is lower. Then all of a sudden here, between -1 and 0, there's another point of intersection. Okay, because they've switched again. Then we have bigger here, then all of a sudden that becomes smaller, and it stays smaller. So we have a third point of intersection. So we know that there's 3 solutions to this system. Okay, now 6 says a system of 2 linear equations has no real solution. What can you conclude about the 2 lines? Well, if I graph a linear equation, it's a straight line that keeps going. The only way they're never going to intersect is if I have another one that's parallel. So we know they're parallel, which means, and I can't spell parallel, parallel means they have the same slope. Alright? So number 7, okay, says Debbie says that the point -1, 3 is the only solution to this system of equations. Explain why her solution is or is not correct. Okay, first thing I would check, do they work for both? So if I plug in 3 for y and -1 for x, does it work out? 2 times -1 is -2, minus 1 is -3, over -1 is a positive 3. Okay, so that one worked. Now let's try this one. 3 for y, 1 plus the square root of -1 minus 1. -1 minus 1 is -2. 1 plus the square root of -2. That's an imaginary number, so that one definitely does not work. So why isn't it correct? Because it doesn't work for both. Okay. 8 says solve the system defined by these 2 equations. So once again, I'm going to jump to Desmos and do that one. Okay. Alright, so I graphed it and we noticed a few things. First of all, this exponential, or not exponential, this rational has those asymptotes, right? And it jumps. So the way this graph is set up, it actually will never touch. Okay, so we would say that there is no solution because they never intersect. If they never intersect, they never have a solution. Now 9. A right triangle has a hypotenuse of 37 centimeters. The length of one leg is 3 times the length of the other. What is the area of the triangle? So 3 would be 3 times x, and we have x. So we set up our, it's a right triangle, so a squared plus b squared equals c squared. So I have 37 squared equals 3x squared plus x squared. Now, we're talking about systems of equations, so I can simplify this to 9x squared plus x squared, which would then, we would add together to be 10x squared. Okay. And then I could find the square root of 37, or square 37, 37 times 37. Okay. The other thing I could do is set these two equal to each other as equations and see where they intersect. Since we're talking about solving a system of equations, we could do that way, find out what x is, and then use that to find the area. Okay? Or I suppose I could even do it even different. If we really wanted to, I could subtract this 10x by 37 squared. That I would know would be, would that help me out though? No, I don't see that helping me out. So let's do that. So, I had to zoom in a bit, but here's my answer. So we're looking at the x value. So 11.7, okay, is what we would want. Because that's 37 squared is 1369. This is where they equal. Now this went down and curved back up. So we can't have a negative distance, so 11.7 would be x. So if I know what x is, then using the formula for area of a triangle, I go 1/2 times base times height. So 3 times 11.7 would give me 1, 2, 5, 350, 35.1 times 11.7. So then I just multiply that out and go 1/2 times 35.1 times 11.7. And we get our area of 205.335 centimeters squared. Okay, last one. The period of a pendulum is given by the lowercase Greek letter tau, which kind of looks like pi with missing a leg, and depends on the length of the pendulum, and the pendulum's gravitational acceleration g according to this formula. For what lengths in meters is the period of an earthbound pendulum numerically equal to 4 times the pendulum's length in meters? The gravitational acceleration for an object on Earth is about 9.8 meters per second squared. Okay. Is the period, of an earthbound pendulum numerically equal to 4 times the pendulum's length? So we go 4 times L. We want to know when that's equal to this, right? Okay, now the pendulum's gravitational acceleration would be 9.8, so we put 9.8 here. So if I split this up and make this 4x, y equals 4x, and y equals 2 pi square roots of x over 9.8, we should be able to graph them both, and looking at where they're the same, and that'll tell us the length. Let's try it. So whenever you have two things equal, you can always split up either side, set them as graphs, using graphing software. So if I look at this, there's two options. There's 0, 0, and 0.25, 1.007. Okay? So if we zoomed in, it would look like that. So 0, 0, okay, because if x's were zeros, they'd be equal, but that's not going to help us. So a pendulum would have to be 0.2518 meters, because length in meters. Okay? So that's the value of x. There's our answer, and there we go, guys.